Calegari from Chicago, and she will be talking about laminations and external angles for similarity pairs.
Okay, thanks very much. Thank you to the organizers for putting together a great conference. And a title which didn't offer a lot of guidance to the speakers about what to talk about. So I'm giving a talk. I mean, I asked one of the organizers at some point what I should talk about, and they sort of said, oh, whatever you want. So I'm giving a talk, has nothing to do with groups. It's a talk in complex analysis, or complex dynamics. So there. Anyway. All right, so, but, you know, it's got some things in common with some of the themes of this conference. Laminations are going to make an appearance. Hyperbolic dynamics is always at the back of everything, as it is in many of the talks of this conference. And the word quasi will turn up at some point. All right, so one of the nice things about the field, so complex dynamics for me is always in one complex variable. So dynamical system, usually finitely generated by a collection of holomorphic maps between subsets of the Riemann sphere or some Riemann surface. And there are many classical examples of complex dynamical systems with very rich and important theories, with big kind of connections to all kinds of important things in topology and geometry, group theory, differential equations, so on and so forth. Two of the very well-known theories are theory of Kleinian groups, which, if you want to think of it in this way, is a theory of hyperbolic three-manifolds, and the theory of rational maps, so endomorphisms, holomorphic endomorphisms of the Riemann sphere, and they're sort of the dynamical system generated by iterating such a map, or maybe sometimes family of maps. And these theories, each individually very deeply sort of studied by many people. There's a lot of beautiful structure and interesting phenomena. But one of the interesting things is the existence of kind of, people sometimes talk about dictionaries or correspondences between phenomena in the world of, say, Kleinian groups and phenomena in the world of rational maps. And sometimes it's kind of mysterious, and for this sort of technology transfer, one suggests an idea in one field suggests something to work on in the other. Sometimes the correspondence is not exact for interesting reasons. So I want to talk about a theory, sort of a arena to do complex dynamics, which is neither of these two things, not the theory of rational maps, not the theory of Kleinian groups, but a kind of, I don't want to call it a toy example, but a sort of a simple, sort of stripped down example, which ends up having kind of pretty interesting connections to both theories. So if you're interested in hyperbolic three-manifolds, or you're interested in theory of rational maps, then I think this is actually a fruitful domain to study. And so looking at this idea of, well, we want to sort of look at analogies that structure in one of these domains. Maybe we look for an analogous structure in another of the domain. The objects I'm looking at and trying to talk about today are the analogs of what in the theory of Kleinian groups are ending laminations associated to sort of possibly partly degenerate Kleinian groups, or what I don't think even there's a canonical word for it. People tend to call it the Thurston lamination. I'm just going to say the impression lamination for a rational map. And so here one has a picture stolen from Wikipedia of Doherty's rabbit. So this is the Julia set of a quadratic polynomial endomorphism of the Riemann sphere, and it's connected, and its frontier is the image of a circle. If you uniformize the complement of this as the unit disk, this Julia set is locally connected, and so the uniformizing map extends continuously to a surjective map from a circle to the frontier of this sort of wiggly shape. It's not injective. Some collections of points can be kind of collapsed. For instance, something coming in here, coming in here, coming in here are all kind of crushed to the same point. So you have finite collections of points in the circle are identified to a single point in the frontier of the Julia set, and so that can be recorded by drawing a lamination on this sort of abstract sort of parameterizing circle. And then these laminations turn out to be much easier to study sometimes than the original map, because they're invariant under much simpler kind of dynamics on a real one-dimensional manifold, namely the circle. So that's sort of the idea, rational maps, and we want to look at something completely analogous, if you have that picture in mind, in another context, the context of similarity pairs, and I want to tell you now what that is. So very, very simple objects, so simple you may wonder if there really is any interesting theory associated to them. So I want to talk about not a single dynamical system, but a space of dynamical systems, a kind of family of dynamical systems parameterized by a single complex number c, which is going to have absolute value less than 1. So we're going to fix c. C is the parameter associated to the dynamical system. So having fixed the parameter c, we define the following dynamical system. It's generated by two maps. Well, they're not very complicated maps. F takes z to zc plus 1. G takes z to zc minus 1. I noticed David Fisher said z yesterday. I think he just did that for fun. But anyway, two maps. Simple as possible they could be. Two linear maps of the complex plane with the same stretch factor, and simply with two different fixed points. Well, any two such maps with the same stretch factor, we could conjugate to make one of them of this form, zc plus 1, zc minus 1. It doesn't matter what these two constants are, but any two different constants would give you kind of conjugate dynamical systems. And G, capital G, is simply the semigroup generated by little f and little g. So just apply f and g in some order over and over and over and see what happens to points in the complex plane. And since the absolute value of c is strictly less than 1, this is uniformly contracting, and so it's sort of a hyperbolic dynamical system. And the basic question is, well, okay, so for each parameter, little c, we get a dynamical system. How does the dynamics depend on this parameter? All right? Well, so what's a way of talking about the dynamics? Okay, so if you have a dynamical system, it tends to be uninteresting to look at points which, when you apply the dynamics to them, they wander off and never come back. What turns out to be a more interesting thing to do is to look at the subset with the property that when you apply the dynamics to points in that subset, well, they keep coming back, maybe in an interesting way, to where they are. So where the dynamics is recurrent. And when you have this sort of hyperbolic sort of dynamical system uniformly contracting, there's a kind of a canonical set that one tends to pick out, the attractor of the dynamical system. In this context, I'm going to call it the limit set by sort of analogy with theory of Kleinian groups. It's the unique, compact, non-empty subset of the complex plane, forward invariant under G, meaning that it's equal to the union of its images under the generators. So lambda is equal to f of lambda and g of lambda. So what do f and g do? Each of them just takes the complex plane, shrinks it by some factor, rotates it by some angle, and then moves it to the left or moves it to the right. So they shrink and dilate, shrink and rotate by the same factor. And so f lambda and g lambda are sort of isometric copies of themselves. They're the same. They differ only by a translation in the complex plane. So the limit set lambda has the property. It's made of two smaller rotated copies of itself, one displaced sort of to the left, one displaced to the right. Here the left seems to be left and up a bit, but that's okay. So here you can see lambda, the entire kind of squiggle here, is made of sort of two copies of itself, a blue squiggle and a yellow squiggle. And the blue squiggle is, well, if we take this thing and rotate it a little bit and shrink it off to the side or shrink it off in the other direction, we get the two copies. All right, so that's what the limit set is. So, well, I drew a picture. So how did I draw a picture? You need to have some kind of numerical method to get a hold of something like that. So how do you draw a limit set? Well, so the limit set is the unique compact non-empty subset of the complex plane forward invariant under G. So all you need to do is draw any compact, non-empty subset of the complex plane forward invariant under G, and that must be lambda. So how do you find such a set? Well, you find a set which is big enough that it's going to contain lambda, but maybe it's too big. So big that it's not quite forward invariant, right? F and G both shrink it. So it's so big that it contains lambda, and then so you replace it by its forward images, and you maybe get a slightly smaller, slightly better approximation to lambda, and then you replace that by its forward images under F and G, and that's a slightly smaller, slightly better approximation to lambda, and you iterate, and the nested intersection of all this thing is, in the end, well, compact, non-empty, forward invariant, so it has to be lambda. Okay? So the thing to do is simply take a disk D big enough that its images under F and G are contained inside itself. And then for each n, we have a sort of an nth approximation to lambda, which is as follows. Look at all words of length n in the generators little f and little g, and look at the forward images of this disk under those generators, and take the union of them. So this is 2 to the n little disks, each with size 2 to the minus something. No, absolute value of c to the n, I guess. And so the union of these, well, so the point is D contains f of D union G of D, and f of D contains f of D union fg of D, and G of D contains gf of D and gg of D, and so on and so forth. So this set here is contained inside Gn minus 1 of D and contains Gn plus 1 of D. So these are a nested sequence of compact sets. And so the intersection of all of them is compact, non-empty, and by construction sort of forward invariant, and therefore is equal to lambda. So instead of just drawing lambda, we simply draw Gn of D for some big n and argue that that has to be close enough. So here's an example. Start with D. Take the images of the images, and so on and so forth. There's some interesting combinatorics that comes out of this. We can kind of build a graph. Here it's sort of a tree which comes from when these images sort of overlap. And we can take a vertex for each image and join them by an edge and so on and so forth. And so some interesting combinatorics here that I kind of don't want to go into, but keep iterating. And after a while, you get a picture, and then you keep iterating, and the picture sort of looks more or less the same no matter how often you iterate, so you declare that you're done, and that's the limit. Okay. So there's sort of some interesting phenomena that at this stage, if you look at a few examples, you might say, well, here's some interesting things we want to pay attention to. So if we want to understand this dynamical system G, we have this limit set which is associated to it, and then it's very natural to ask, this is a compact subset of the complex plane. Well, what topological properties does it have? How do its topological properties depend on the parameter little c? So the most obvious, the first thing that you might ask is, well, what about the connectivity of this set? Is it connected or not? So here's an example in which it looks connected. So maybe you hope in this particular case this limit set is connected. So you can ask the question for each parameter little c, is the limit set of the dynamical system associated to that parameter, is it connected or not? And so Barnsley and Harrington asked this question, and they asked it sort of, this is already by analogy with the theory of rational maps in the maybe best studied case of complex polynomials of the form z goes to z squared plus c. Associated to such a rational map, one has what's called a Julia set, the analog of a limit set, and the Julia set could either be connected, it turns out, or totally disconnected, a Cantor set, and the set of parameters for which the Julia set is connected is called the Mandelbrot set. And so here we're in a slightly different context. Instead of one polynomial of degree 2, we have two polynomials of degree 1. And that's just sort of more or less as good. And so the Barnsley-Harrington Mandelbrot set, script n, defined by sort of perfect analogy with the usual Mandelbrot set, is simply the set of parameters. So it's a subset of the unit disk by fiat. We want our thing to be uniformly contracting. So complex number of absolute value strictly less than 1, for which the associated dynamical system has a connected limit set. And so there's some nice equivalent definitions, it turns out. To be connected turns out to be equivalent to f of lambda intersect g of lambda is non-empty. Well, of course, this is necessary. I mean, if f of lambda and g of lambda, lambda is f of lambda union g of lambda. And so f of lambda and g of lambda are compact subsets of lambda, so if they don't intersect, you've just exhibited that lambda is not connected. So of course, this is a necessary condition, but it turns out to be sufficient. So to speak, the biggest gap there can be between a subset of lambda and the rest of lambda is the gap between f of lambda and g of lambda. So if f of lambda intersects g of lambda, everything somehow intersects everything else, and it's connected. All right. There's two other kind of characterizations here, which C here restricted to be of absolute value strictly less than 1. Turns out to be in this so-called Mandelbrot set is equivalent to being a root of a power series whose coefficients are in the set -1, 0, 1. And if you don't like power series, you should still like polynomials. And so, well, we can't guarantee that C is a root of a polynomial, but it's a limit, can be approximated by roots of polynomials with coefficients in -1, 0, 1. I find this a little bit surprising or counterintuitive. We started out doing complex dynamics, and all of a sudden we're talking about roots of polynomials. I think this is sort of one of the attractions of the subjects and one of the reasons that this particular variant on theory of Kleinian groups or rational maps is especially sort of worth study. And I thought I'd just indicate why this is true, because it's quite simple and I think a kind of a nice fact. So remember, what did f do, if I remember? So f took alpha to z alpha plus 1, and g took alpha to z alpha minus 1. Pardon me?
Just that alpha was z and...
Alpha was z and z was c. Yeah, so now let's... All right, that's good. C. Is that better? I've substituted alpha for z. I think I'm allowed to do that. I just don't want... I'm going to get a power series, and the variable is going to be c. So I don't want z to be the constant in the power series. All right. So anyway, so we have these two transformations, f and g. And so what does it mean to be in the limit set f lambda? Well, what does it mean to be in the limit set lambda? Well, to be in the limit set lambda means we keep applying f and g over and over again. We stay in lambda. So a point in lambda is any point after you apply f and g to it over and over again infinitely many times, so to speak.
Actually,
Yes?
is there any particular reason for choosing this pair?
It's the simplest non-trivial example, but I can say a little bit about that in a second if you like.
If you change it like a -1 to -2, makes no difference.
Well, as I said, having the choice of these two constants here, up to conjugacy, we could make them any two different numbers. So, I mean, 1 and -1 are a nice choice of two different complex numbers. Makes no difference.
How about 3? The 3 maps, is it similar?
3 maps is similar, but slightly more complicated. But if you like, I can say something about that in a minute. But for now, let me just say something about 2 maps. But sure, you can have any number of maps, and we can say more about that in a sec, perhaps. All right, so to be in the limit set means that your number obtained by applying f and g an infinite number of times in some order. To be in f of lambda means first you're in lambda, and then you apply f. So in other words, to be in f of lambda means we've applied f and g some infinite number of times, but the very last thing that we applied was f. To be in g of lambda means we've applied f and g some infinite number of times, but the very last thing that we applied was g. Okay? So what happens if we just apply f and g a number of times? Well, we start with alpha. Let's apply f. We get c alpha plus 1. Let's apply, I don't know, g. We get c squared alpha plus c minus 1. We apply f. We get c cubed alpha plus c squared minus c plus 1, etc. And what you sort of see is that I'm writing it in kind of reverse order. It's a little bit annoying, but I'm generating a kind of a power series so to speak. So maybe I apply this some further number of times, and, well, maybe I've got c to the n alpha plus c to the n minus 1 minus c to the n minus 2 plus c to the n minus 3 plus dot, 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 dot. But then I'm going to have like plus c cubed minus c squared minus c plus 1 if the last few things I applied were g, g, f, so to speak. So if what I'm applying in order tells me simply whether the coefficient is plus or minus 1. So after I've applied infinitely many things, c to the n alpha recedes off into infinity. C to the n goes to 0 because c is absolute value less than 1. So I simply get a power series in the, variable c where the coefficients are 1 or minus 1 depending on whether the kth last thing I applied was f or g. All right? So in order to be in f of lambda, so f of lambda is just the set of things of the form, well, I have to start with 1, plus or minus c squared, plus or minus c cubed, plus or minus c to the 4th, plus or minus dot, dot, dot. And to be in g of lambda, I'm minus 1, plus or minus c squared, plus or minus c cubed. And if f of lambda intersects g of lambda, something here is equal to something here. So if f of lambda intersect g of lambda non-zero, implies, in fact, it's equivalent to saying the difference between something here and something here is 0. Well, the difference between these two things is 2. The linear coefficient is 2, 0, or minus 2. I'll just say plus 2, 0, or minus 2c, plus 2, 0, or minus 2c squared, plus 2, 0, or minus 2c cubed, plus dot, 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 equals 0. Well, I divide through by 2, I get 1 plus 1, 0, minus 1c plus 1, 0, minus 1c squared plus dot, 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 equals 0. In other words, some power series with coefficients in 1 or minus 1 is equal to 0. I mean, you look at the first one that's non-zero and you divide through by c to that power and whatever. Okay, so this is kind of cool. And then a power series you can approximate by polynomials. So this is kind of cool. So if you care about roots, you could have just simply started out with the following, perhaps, question, not motivated by complex dynamics at all. What does a root of a polynomial look like if I know its coefficients? If I simply know my polynomial has, say, coefficients 3, 7, and 46, and 46 never comes after 3. That's a kind of polynomial. Well, you get a bunch of polynomials, you get a bunch of roots, you plot all the roots in the complex plane, and to your surprise, you get this sort of beautiful fractal object. You're going to sort of see an example in a minute, and you'll say, well, where on earth did that come from? And what I'm telling you is that where it came from is complex dynamics. The complex dynamics associated to families of linear polynomials have parameter spaces, which are closures of sets of roots of polynomials satisfying, well, we could say automatic conditions on their coefficients, if you like that fancy word, but constraints on their coefficients of the form that the coefficients are forced to lie in a particular set.
So when you say automatic, you're saying you're referring something about finite state automata.
Yeah, I didn't need to say that. Well, I just group theory audience, whatever. Anyway, so I think this is kind of an interesting thing. So you can maybe you care only about roots. Maybe that tells you if you care about roots, you should care about complex dynamics. So I think that's kind of cool. But anyway, that's the last time roots are going to come up in this talk, but it's part of the motivation. So here's a picture of this Mandelbrot set M. It's kind of interesting. The color here has to do with how hard the computer worked. I guess it ran out of ink or something. So it's a subset of the unit disk. Being colored in means you're in M. So the big white blob in the middle is not in M. When the absolute value of C is small enough, the limit set is disconnected. If it's disconnected, it's just a Cantor set. You can probably believe that yourself. And anyway, so there's sort of big gap in the middle. But otherwise, it looks like this kind of like annulus with crinkly edges, except there are these two little spikes on the real axis, the negative and positive real axis. These sort of spikes come in. We refer to these spikes as whiskers. They really are there. They really do intrude. They really are isolated. The whiskers themselves have no hair on them. So an interesting thing, if you're a root of a polynomial with coefficients in 1, 0, and -1, and you're real, and your absolute value is closer to a half than blah, 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 you can't be approximated by a non-real root of such a polynomial. That's kind of interesting. But anyway, not so hard to show dynamically, but it's maybe a bit harder to show if you're talking in terms of roots. Anyway, so you have this nice picture here, and it's kind of crinkly and fractally, and you maybe want to zoom in and take a look at some of the phenomena. Well, to do that, you need to draw it numerically. And so let me just make the following observation. It's easier to draw the complement because to fail to be an M, for f of lambda to be disjoint of g of lambda, and since capital G sub n of d is an approximation to lambda, that's equivalent to saying little f of g sub n of d is disjoint from little g of g sub n of d. And that's something you can detect numerically, and it's an open condition. And so you can find a big open subset. Well, in fact, the complement is open, and every point can be numerically certified by a kind of finite certificate of this kind. So you can recursively generate and prune the tree of pairs of words u and v for which this intersection is non-empty. After a while, that tree might be empty, and you've certified that you're in the complement of M. So drawing the complement of M is not hard. Drawing M sort of rigorously is harder. Anyway, that's numerically. Drawing M rigorously is a bit harder because the set M, it's a closed set, but it's certainly not, well, it's a closed set, it's not open. However, it turns out it has a lot of interior. So interior is good because when being in a set is something that has a property that has interior, then it's sort of a numerically stable property that you can certify rigorously. And so it turns out that M, although the interior of M is not quite dense, it turns out the interior of M is dense away from the real axis, so away from those two whiskers, with the sole exception of those two whiskers, which can just be drawn by hand if you like, the interior of M is dense. So this was conjectured by Christoph Bandt and myself, Sarah Kirk, and Alden Walker proved that a couple of years ago. Oh, so by the way, when I finally get to talking about some recent work, it's all joint work with Alden Walker. Okay, I think I had it on my first slide. So the proof is constructive, and you can numerically certify that given open regions are contained in M. So you can build M and its complement sort of rigorously and numerically and draw good pictures. Okay, so when I say you can do it, this is not one of these mathematician's version of can where it's sort of there's an algorithm. There really is an algorithm. So here's a computer program you can get to from Alden's website, and it's just a kind of a Java applet which lets you sort of zoom around in the parameter space. So here we have the parameter space here. The blue bits are in M, and on the left, for a given coordinate here, a little red dot here, you've got the corresponding limit set. So over here, sort of corresponding sort of limit set. So anyway, so around here there's whatever it look like I'm kind of. So it looked like I'm kind of in the interior here, and the two sets seem to intersect. But that might be a numerical kind of whatever. If I zoom in at this point, so you zoom in, some interesting things occur, which is that numerically, you start to notice some interesting things. You might have thought this sort of annulus was a nice solid annulus, but if you zoom in sort of with high enough resolution, there turn out to be these bizarre little exotic floating holes, and kind of correspondingly on the limit set side, we can see that there's sort of pairs of limit sets which, so they're the power of numerical methods to crash. You can see, I'm not sure if you can sort of see it that well, if you zoom in, these blue set and the red set, they come very close to touching, but they don't actually touch. So they really are sort of disjoint. You really are in the white region here. But you notice that these sort of blue and red regions here, yellow has now become red, I guess. this blue and quote-unquote yellow region here have developed all these sort of intricate kind of gear-like patterns, and the gears on one have sort of interlocked with the gears on the other, and it looks quite reasonable to say, well, this gear here, blue guy here interlocking this red one here, there's no way you could extricate that. There's no way you could sort of pull the blue guy out from the red without crossing the red on the way. Well, that's sort of an intuition. Of course, this blue set here, it's not solid. It is a Cantor set. This red set here is also a Cantor set. There's no topological obstruction. But somehow, geometrically, this limit set knows that it's pretty close to being this solid set, and you can't pull the blue guy out without bumping into the red guy, and that says you can't take this red point here back to the big kind of disconnected component without crossing through the Mandelbrot set M. So this hole is a genuine thing, it turns out, and let me just try to put the parameter down to whatever. And then if we sort of zoom sort of further in, well, I don't know if you can see, but there's maybe that goes over here. This is the power of my computer sort of conking out. One thing that you might have seen if I'd chosen a good numerical value or something is that circling this big hole, there are some smaller holes. And I don't think they're going to make an appearance today, but that's okay. No, all right, fine. And that kind of corresponds to a sort of tuning operation one can perform on these limit sets, in which this phenomena that you had of one guy's linking the other occurs sort of somehow at the next level down in this self-similar structure and these things. All right, so there are some pictures here that you can sort of see this phenomenon more clearly. I was looking in the wrong place. So here's, you've got the hole I just looked at. You can see a few little islands here, tinier holes circling this other hole. And if you went to one of these tiny islands and zoomed in on this, you'd find smaller islands around that, and so on and so forth. Here's an example that's a little bit more clear. We've got a bunch of holes here, kind of accumulating an interesting spiral. Here we've got holes and then holes on holes, and so on and so forth. So the structure is, in fact, quite intricate. The topological structure of M is certainly not what one might expect by drawing a pretty good but not excruciatingly detailed picture. At quite fine resolution, it looks like a solid annulus, but after all, it's not. And so here's the example you just saw. These two guys are linked sort of geometrically, but they don't touch. So this is a phenomena which is perhaps unfamiliar to people working in complex dynamics, where we, the sort of literally the shape as distinct from, say, the topology of the pair of sets ends up exerting a big influence on sort of what happens. All right. So it turns out that M, in fact, rigorously one can show has infinitely many holes. And in fact, we can make a much stronger conjecture than that. Myself, Sarah, and Alden conjecture that holes accumulate on every point in the frontier of M, again, away from these whiskers. And this is related to a conjecture, sort of number theory conjecture. So the set M is a closure of a collection of roots. However, it's not immediately obvious, or even it's not, in fact, it's very hard to sort of decide whether you can actually find interesting algebraic points in the frontier of M. So we conjecture, in fact, that algebraic points are dense in the frontier of M. And these conjectures are related in the following way. This self-similar structure here in the parameter space, where you have this kind of spiraling of holes around a limit, has to do with a certain kind of renormalization operator one can do on these dynamical systems. The fixed points of these renormalization operators are algebraic in the parameter space, and they generate a kind of an approximate self-similarity in the parameter space. So one can show that a given point is a limit of small holes by finding a decent-sized hole and then proving that its images under these renormalization operators are littler holes accumulating to the limit. So one can, at the same time, prove both that a point in the frontier is algebraic and that it's a limit of holes. Holes are white. Blue is the Mandelbrot set. The white thing are the holes in the Mandelbrot set. The conjecture is that the holes are dense in the frontier. So every point should be a limit of holes, very small holes. And conjecturally, there's a dense set of algebraic points in the limit, in the frontier, excuse me. All right, so we've talked a little bit about M and L, and so what I want to talk about, maybe some new stuff today. Once we know that lambda is connected, well, if lambda is not connected, it's just a Cantor set, and that's the end of the story. If lambda is connected, there's sort of more refined topological questions we could ask. For instance, we could ask, does it have cut points? This turns out to be very much the right question to ask when you're talking about, for instance, Julia sets of rational maps, or for that matter, limit sets of Kleinian groups. Anyway, so this is the question I was asking, the algebraic points dense in the frontier. And then again, give a simple topological model for the dynamics of G on, here, the boundary of lambda. Well, what do I mean by the boundary of lambda? Lambda is just a set. Let me see if the next slide is any good. So here we go. So what I'm going to do is, if I've got a parameter for which my limit set's connected, so here it is, it's connected, it's not hard to show that if it's connected, it's locally connected. So the complement, it's got some little maybe holes in the middle, but there's one unbounded complement, which is basically a punctured disk, and you can uniformize that unbounded complement as the complement of the unit disk in the complex plane. So the complement of the unit disk in the complex plane uniformizes sort of the big outside component. And it comes together with a continuous surjective map from the circle to what I'm going to call the boundary of lambda. It's really lambda with all the little holes in the middle filled in. Lambda itself might have some holes. So really this means the boundary of lambda means the frontier of like lambda with little holes, bounded holes filled in, sometimes called the filled limit set. Okay? So you can sort of see it here, and I've got the blue side and the yellow side. And it's sort of not completely transparent, but it turns out to be the case that we can divide the circle into two pieces, sort of a JF side and a JG side, so that the JF side parametrizes boundary in the F side, and the JG side parametrizes boundary in the G side. Yeah, just as it is in this case. So you might say, well, that must be obvious, except the problem is, really you need to say something about, we need to be in the frontier. The point is, if we have a parameter which is not in the frontier of M, F of lambda and G of lambda could overlap rather than somehow just bump up against each other. If they overlap, there might be a kind of big region they have in common. And then, well, points in the frontier of that, how do we decide whether they're in the F side or the G side? We can't. And in fact, the subset that they overlap might not even be connected. It might have bits poking out all over the place. So there might be no natural choice to parameterize your circle and decide what's in the F side and the G side. But if C is in the boundary, then this can be done. So let's just assume that our circle has been divided into two pieces, sort of one mapping to the F side of the boundary and one mapping to the G side. And so there's some dynamics on S1. Where does the dynamics come from? Well, so F and G take the limit set to itself. So the frontier of the limit set is contained in, but not necessarily equal to, F of the frontier union G of the frontier. So there's a subset of the frontier whose image under F is the F side of the frontier, and there's a subset of the frontier whose image under G is the G side of the frontier. And they correspond to connected intervals in the circle, which I'm going to call I sub F and I sub G, which are the domain of definition, if you like, of the map F and G restricted to the boundary circle. Well, it's not a boundary circle over here, but we've pulled back the dynamics to a circle. So what we have is a dynamical system on a circle generated by two maps F and G, whose domain of definition is not the entire circle, but a big subset I of F and a big subset I of G. And what do F and G do? They take these big subsets and they shrink them down to the left side and the right side, respectively. So you've got a dynamical system, one-dimensional dynamical system on the circle. Well, not defined everywhere. And so now I want to talk about this lamination, the dynamical lamination. The F side here, J of F, this blue left-hand side, and the yellow side here, I'm going to divide that by a leaf. I'm going to call it script L. what I'm going to do is I'm going to look at its images under F and under G. Well, I can't do that unless it turns out that both endpoints of L happen to be contained in the domain of definition of little f and the domain of definition of little g. So if they are contained in the domain of definition, then I can apply f and g, and I get f of lambda and g of lambda. Otherwise, I can't. So if lambda is a leaf with both endpoints in the domain of definition of f or in the domain of definition of g, we can apply f or g to get a new leaf. And being in the domain of definition exactly implies that the images don't cross L, because they get taken to the f side or the g side. So here, both are in the domain of definition, and f of lambda and g of lambda are defined. Well, we can keep on going. We can, each time a leaf we've produced is in the domain of definition of f or g, we can apply f or g to it, and we get a bunch of leaves as descendants. And if we didn't have any intersections so far, then we push forward that joy, and so these leaves are all disjoint, and we get a collection of leaves in the circle, and so none of them cross. Okay. So this is, we're going to call it the dynamical lamination. So roughly speaking, the dividing side here, the original leaf L, corresponds sort of to a shortcut in lambda, solid lambda, from one side of the intersection of the f and g to the other. So this sort of cross-cut here between these two red dots, that's roughly speaking what L corresponds to, and the images of it correspond to these other guys over here. And so they're breaking up sort of filled lambda topologically in a kind of tree structure dual to the tree of the lamination, or equal to the dual tree of the lamination. So here, an example, dynamical lamination at depth 6, just so you can see that, well, you get the same kind of pictures that you'd get if you did a rational map or a Kleinian group, probably indistinguishable to all but the expert. So having two maps is a little bit annoying, and so it's convenient in one-dimensional dynamics to have a single map that we iterate. So we can sort of repackage this by looking not at f and g, but looking at their inverse. After all, the image of f and the image of g are disjoint. So if you have a point, and you want to know whether it was the image of f or g, there's only one possible choice. And so we simply define a new map, capital H, to be equal to the f inverse of x on the f side, to g inverse of x on the g side, and sort of undefine at the top. So it takes the blue and the yellow and stretches them to this big blue and this big yellow. So it's a single map of the circle to itself. So it's discontinuous, but that's okay. Piecewise continuous. And you can iterate this map. And then the dynamical lamination is invariant under this map. Okay. And so using this map and this dynamics, it turns out we can exactly capture the cut points. So cut point is going to correspond, well, to a pair of points on the sort of parametrizing circle that map to the same point in lambda. So they correspond to, say, a leaf over in this circle, and we can characterize what things occur as leaves. Well, the leaves corresponding to cut points are precisely those leaves for which the dynamics is defined for all time. So we've got this single map of the circle to itself. If I can draw a leaf with the property that I can just keep iterating the map H on it forever, well then it corresponds to a cut point, if and only if. This is not so hard to see because, well, what is H doing? It's sort of the inverse of f and g, f or g. And f or g, what do? Well, they shrink things. So if you could apply the inverse infinitely many times, what that means is you've been shrunk infinitely many times already. Well, if you've been shrunk infinitely many times already, your diameter is 0, which is to say you're a cut point. Yeah? All right. And notice these things can't cross the dynamical lamination. So when the dynamical lamination is big, it gives you some big constraints.
So is the Cayley tree of the free group of the free semi group on two generations lurking in that picture in any way, or not?
Not the whole tree, no, but a bit of it. Yeah, that's sort of the point. It's sort of seeing some but not all of the dynamics, right? You're sort of seeing the part of it that escapes to the frontier, and how much you see is kind of the interesting thing. Yeah, but yeah, if you like, and it gives you planar structure in that subset. So that's fine. This is a nice theorem. We say when there are cut points in terms of dynamics, but it's not very practical. How would you implement this on a computer? So there's a nice criterion to check, it turns out. So let's talk about interaction. So we say two leaves interact in two cases. Either they cross or one sort of hides the other from L. So here they interact. They cross. This one hides that one for L. These two don't interact. They've got their own little empires that they're jealously guarding. They have nothing to do with each other. So here is how you can tell whether there are any cut points or not. So let's let L sub f be f inverse of capital L if it exists. So let's look at the leaf of the dynamical lamination. So the dynamical lamination, it's generated iteratively. Each leaf has a depth, which is how many steps we went through to get to it. Let's look at the leaf of least depth which interacts with L of f. So part of the theorem is that such a leaf exists. Then we can tell exactly whether there are cut points in lambda depending on how they interact. So if mu hides L of f, there are cut points. If mu crosses L of f, there are no cut points. And it turns out L of f can never hide mu. So we just look at the first leaf mu, which interacts with L of f. There is such a leaf. And then looking at it, whether it crosses L of f or not, tells us precisely whether there are going to be cut points. So we can sort of answer the question numerically in a pretty fast algorithm, actually. All right. So here's an example. Here, mu and L of f, mu hides L of f, so there are cut points. And just as we saw, well, maybe I don't know. So this point here looks like kind of a cut point. This is an example where we saw some cut points before. So there are cut points. Here's another example. Mu and L of f, when they first interact, they cross. There are no cut points. And you can see this sort of filled limit set is kind of stubby. There's no obvious, topologically it's just a disk. All right. So the set of all cut points has a nice recursive structure. It's parameterized by, roughly speaking, directed paths on a directed graph. So algorithmically, from the dynamics on the circle, you can build a directed graph. We're going to call it capital I of G. And you can look at the directed paths, infinite directed paths in this I of G. So whenever there's, for instance, a directed cycle, you know that there are infinite directed paths. And once you have constructed I of G, the set of infinite directed paths in I of G precisely parameterizes the set of cut points in lambda. So you have a kind of complete description of topologically what this sort of filled limit set is in terms of this combinatorial data. So I of G is sometimes a finite graph. If it's a finite graph, then everything you need to know about that particular limit set you know just by looking at that graph, topologically at least. And so conjecturally, the set of values for which this is finite is open and dense. And this is supported by computer experiment, actually. All right. Certainly, there's some examples, kind of analogs of renormalizable points there where it could be infinite. But, anyway, those should be pretty rare. So here's the graph associated to this guy. And in fact, walks in the graph correspond to kind of dynamics on the set of cut points, right? And we have a periodic orbit, of course. Well, any directed path concatenated with an infinite path is an infinite path. So walking on the graph, you kind of get a map on the set of, cut points. And so the dynamics on the cut points kind of reflected in the dynamics on this graph. So this is a nice kind of combinatorial model. I wonder whether there's a precise way to make a connection with some of the combinatorial models for Julia sets developed by Laurent Bartholdi and Nekrasevich and their kind of collaborators. I think that's sort of, probably the answer is very likely, and it would just take an interested grad student to work it out. So there you go. If you're interested in group theory, there's a connection. Yes?
So this whole thing hinged on that your interval being in the domain of definition for both F and T.
Yes.
Do you have a good understanding of which C this occurs?
Numerically, it's certainly not generic. I mean, if there is no L, then there are just no cut points. So that's sort of a degenerate case. Yeah. So I mean, yeah. No, I mean, so that case is sort of special. That's sort of the degenerate special case. That's certainly, we know exactly. In that case, the thing is just a field. So it's just topologically a disk. Yeah. And that can certainly happen. So here's some examples and some interesting phenomena. And I think understanding relation, for instance, between spectral data on this graph and Hausdorff dimension in these limit sets is sort of another interesting problem. So this is all well and good, but in the end it did depend on being able to look at the dynamics of this transformation H on the circle. And one thing I've swept under the rug is, well, how exactly did I do computations with H? I mean, if you like, I uniformized the complement of a set, and I pulled back the dynamics of F and G there, and blah, blah, blah. I didn't really do that. That would have been an awful thing to do. That would have taken a dreadful thing. How do I actually compute? How do I, in a practical sense, ever actually do anything interesting with this? Well, this circle parameterizes the boundary. But if I had another circle which was topologically the same circle, for which the dynamics of H was very simple, then numerically I could figure out what was going. So what we would like is to have coordinates on this circle for which the map H is as nice as possible. What's the nicest possible map in one-dimensional dynamics? Well, it's the one for which the derivative is constant. We'd like to have linear dynamics. Linear here meaning simply that length is stretched by a constant factor. And so the theorem is, in fact, that the action of H on S1 is conjugate to a, well, obviously discontinuous linear action, meaning the blue interval is simply stretched by some factor, the yellow interval is simply stretched by some factor. So the entire dynamics and everything you want to know about the topology of the limit set can be read off from two numbers, the stretch factor lambda, which is between 1 and 2, and then how much you rotate it by after you stretch it, and we're going to call that theta. And so E sub lambda theta is simply the map from the circle to itself, which takes the left side and the right side, stretches them each by lambda, and then rotates them by theta. And so every H arising from this construction is of the form E sub lambda theta, at least up to conjugacy, for some lambda and theta. And now this pair of numbers, lambda and theta, we're going to say are the exact analog of the landing ray parameter on the boundary of the Mandelbrot set, assuming the boundary of the Mandelbrot set was locally connected. Sort of the so-called topological Mandelbrot set. It's exactly the parameter. So in the Mandelbrot set, the parameter lambda is irrelevant. Lambda, so to speak, is always 2. And one only has the parameter theta. Here we have two parameters, lambda and theta. Existence of a semi-conjugacy. Well, if this were a one-dimensional dynamics conference, I'd say blah, blah, Milnor-Thurston meeting theory, Lorentz maps, beta transformations. Anyway, so here is the world of E lambda theta. So theta is a number between 0 and 2 pi, and lambda is a number between 1 and 2.
Danny, presumably you understand how lambda and theta depend on steam.
Well, that's an interesting question. So the set of parameters for which there is a cut point are the green guys. So it's nice sort of diag spike. Within that, there's sort of more structure depending on, like, the complexity of the graph parameterizing the set of cut points. But the set of guys for which there are cut points, this very explicit subset of this sort of parameter plane. And there we go. Answering Henry's question, the set of C in the boundary of M for which the set of lambda and theta associated to C in boundary of M is this set in red. This is sort of maybe a numerical accident. I don't think it should be there. It should be symmetrical on the left and right sides. And if we zoomed in a little bit further, which would cost us a bit numerically, it's got an interesting recursive structure itself. Very interesting subset. We don't know exactly how to characterize it. One of the issues is that the map from the boundary of M to the lambda theta plane is discontinuous. So the image is just some funky set. Well, the boundary of M is disconnected, the image is disconnected. It doesn't imply it's discontinuous, but it is discontinuous. Yeah. So it's some set. So some subset of this plane. So you can see there's plenty of times it lands outside the green region and they have no cut points, but plenty of times it lands inside the green region and you have lots of cut points. So it can happen a lot of ways. In the interest of time, I'm going to skip the examples, but if you want to go to Olden's webpage, you can kind of play with this a little bit. Maybe if I have 2 minutes at the end, I'll do a little example. But maybe one more remark. In the case that lambda equals 2, the left side, the F side, and the G side meet at a single point. In that case, the limit set is a dendrite. In this particular case, it turns out that the dynamics of F and G on the limit set, in a little neighborhood of the limit set, is conjugate, not just topologically, but actually quasi-conformally conjugate to the inverse of a quadratic map associated to a point on the boundary of the Mandelbrot set. So if you actually only care about, for instance, the classical Mandelbrot set and its boundary, for instance, if you're interested in this famous question about whether the Mandelbrot set is locally connected, really a question about its boundary, there's some sense in which we're getting a very strong models for behavior at some subset of the boundary using a analytically much tamer circumstance. Local connectivity in our context is completely for free. So we know that these limit sets here are quasiconformally conjugate to the corresponding Julia sets of these rational maps. We can say a lot about those Julia sets and the rational maps simply by analyzing this sort of simpler circumstance. And so Vance, Solniak, and a bunch of other people have looked at this. So in the interests of a little bit more animation, so here again, if I move around in sort of parameter space here, you can see the lamination starts to occur once I enter the blue point, but here we still have finitely many leaves. And once we enter the red point, we have limit leaves, and the limit leaves correspond to cut points. And so there's kind of a understanding the structure of this space and the kind of way in which the combinatorics of the lamination depend on the parameters lambda and theta seems extremely interesting. So the moral of the story is, I think, that the boundary of M is a very complicated set. Understanding exactly how the topology depends on this, there's an intermediate problem, which is that the set itself is very hard to understand. It's not a nice parameter. But we can kind of embed the problem in another context in which we have an extremely simple parameter space, namely an annulus, and for which the answer is, in principle, some simple kind of linear combinatorics. Okay, so that's the end of my talk.
Is it always a dendrite?
No, so it's a dendrite exactly when the parameter lambda is 2. So if I go back to so every single red dot here is a lambda comma theta for some c in the boundary of M. So the ones up the top, there's a lot of red dust up there at 2. Those are dendrites. Those are exactly the dendrites. Those give you complex dynamical systems which are quasi-conformally conjugate to these degree 2 rational maps. The rest of them, just a bunch of other things. Yeah. The structure of the set for which it's equal to 2, I think I'd like to know what values of theta occur. I don't know. And I'd like to know how to characterize the values of C for which you get 2. I mean, it's a dendrite is the answer, but can one say more, maybe algebraically, for instance, about the condition, in terms of perhaps Diophantine properties of C.
What about the Hausdorff dimension?
So Hausdorff dimension of the limit set is pretty easy to read off as a function of C when it's disconnected. And for points in the boundary, it's the same formula. It's sort of the obvious thing. Lambda is made of 2 copies of itself, each scaled by C. And if you're also in the frontier, they're roughly speaking disjoint. So that tells you exactly what the Hausdorff dimension is. The Hausdorff dimension of the boundary, one of the consequences of our linearization theorem, in fact, is that this sort of measure you get for which the thing is linear pushes forward, roughly speaking, to the Hausdorff measure on the boundary. So that sort of has full support and finite total measure, finite positive total measure is kind of a consequence. Yeah. This sort of goes around the other way a little bit. And again, you can read off what it is from lambda. So there's a simple formula for the Hausdorff dimension of the boundary from lambda, which, because it's a formula, I can't possibly look it up.
Do you know that not all the... So you get things at the top that are quasi-conformally equivalent to things in the boundary of the Mandelbrot set?
Yeah.
You know you don't get the whole of the boundary of the Mandelbrot set?
Yeah, the boundary of the Mandelbrot set, roughly speaking, is the horizontal red line which would go from the top left to right. All values, so to speak, the boundary of the Mandelbrot set is parameterized by a circle,
So the
quotiented out by a
Mandelbrot
certain...
is subjective.
What's that?
So
No, so it's not surjective. It should not surjective in the Mandelbrot set. I mean, technically you have to quotient out by the lamination that you get from the Mandelbrot set and then wonder whether the Mandelbrot set is locally connected or not to know whether you're actually mapping to it. But no, it shouldn't be surjective. Yeah. Which is not to say that you couldn't cook up similar kinds of complex dynamical systems, maybe by varying the setup, as you sort of said, by using more than 2 elements or varying the weights in some way to get a linear, so to speak, model, which is quasi-conformally to what's happening in the Mandelbrot set. That, I think, is much more likely to be true, is if you allow yourself to vary parameters in a few different ways. There's a lot of things you can get, yeah. Yeah?
So if C is a root of a polynomial,
Yeah.
is it special? I mean, do you have some additional symmetry?
Well, so then being a root of a polynomial of this sort of type says that you have a point which has sort of got a finite orbit under a specific word in f and g. Associated to that particular word, there's an interesting operator on a sort of renormalization operator, which is, roughly speaking, you can shrink down on the f side and down on the g side to where these things overlap, and look at the copies, the little copies of lambda and g that you have there, and look for the best value of your parameter which looks like that pair. So there's an interesting kind of, this is this renormalization operator on parameter space sort of associated to these roots, and they asymptotically generate sort of self-similarities of m near those points. Yeah, so that's kind of a interesting phenomenon. So this is an analog of like Miserevich points in the Mandelbrot set, if that's your, yeah, you know, that language.
Great. So the first talk after lunch is at 1:30 today. But let's thank Danny again.